All right. Hi, everyone. My name is Federica Chiti, and I'm a graduate student at the University of Hawaii. Today, I will be talking about the abrupt change in stellar spin down that we see at the fully convective boundary and what the implications are in the context of gyrochronology and magnetic activity. So stellar age is one of the most difficult stellar parameters to get precise measure for. In 1972, Skumanich looked at young open clusters and realized that the older the stars were, the slower they were spinning. So decades later, Barnes coined this term gyrochronology to indicate the idea of estimating the age of a star through its measured rotation period. Today, we have access to many more open clusters with good rotation period measurements, like the ones that I'm showing in this plot. So the rotation period is on the y-axis and the effective temperature is on the x-axis. And these clusters represent great calibrators to actually test our stellar spin models and the period age relationships that they reveal. So here I'm showing you a set of gyrochrons as red solid lines that I have calibrated to reproduce the rotational sequences of these clusters. Now we need three main ingredients to make this happen. So we need a set of initial rotation conditions, which we draw from APRSCO. It's a 10 million years old cluster. Then we chose a breaking law that assumes a Rossby-scaled magnetic field and the mass loss rate that depends, that's set by the X-ray luminosity. And finally, we need a prescription for how the internal angular momentum transport occurs. So as you can see, though, these open clusters do not provide us with a large enough sample of old LOMA stars. And these stars are important because they can help us test the behavior of stellar spin down at the fully convective boundary. Now, the reason why this region is interesting is because of two reasons. So the first one is that gyrochronology is the best tool that we have to measure the ages of these stars. And the second one is that stars on both sides of this boundary have very different internal structures. So by looking at the rotational evolutions of these stars, we can understand whether there are significant differences in the stellar dynamos and magnetic activities of these stars. So what we did was looking at these wide Kirill binary systems that had a projected separation larger than 1,000 AU, and that contained the main sequence star, which had a measured rotation period, and the white dwarf, which provided us an independent age of the system. So the rotation period for the main sequence stars were obtained from a variety of rotation period catalogs, with the majority of them coming from ZTF. And then for the total ages of the white dwarf, we combined white dwarf Kirill models with initial to final mass relations, which gave us the progenitor lifetime. So overall, we achieved total ages with a precision better than 20%. Now here, I'm showing you the results for the youngest stars in our sample. So we still have rotation period on the y-axis and the effective temperature on the x-axis. The gray markers that you see on the left are giving you an idea of the typical errors on the rotation period and the temperature. Then we have these solid lines that represent the gyrochrons that we computed at the bounds of this age band, so between a few million years and 4 billion years. And the region bounded by these gyrochrons is the region of allowed rotation periods according to our models. Then the circles mark the location of our main sequence stars. And then in green, I'm highlighting here the fully convective boundary. So what you can see is that according to our models, there is a steep rise in rotation period at the fully convective boundary. And this feature persists if we go to older ages as well. So for example, here I'm adding an 8 billion year old gyrochron, and here a 10 billion year old. And you see that that feature is still there. So the main takeaway from this plot is that at the fully convective boundary, there is an abrupt change in stellar spin down and a rapid increase in rotation period. Now, this result has two main implications. The first one is that a star with a long rotation period at the fully convective boundary may not be necessarily old. And the second one is that a measured rotation period at the fully convective boundary cannot be uniquely associated to a single gyrochron. So instead, you have a range of gyrochrones that span several billions of years, which all provide you a reasonable match to the observed rotation period. So what this is suggesting is that gyrochrone may not be feasible at the fully convective boundary. However, if you look on either sides of this boundary, our gyrochrone seems to have a normal behavior. So gyrochronology still provides you with a good leverage on the age on the hotter side and on the cooler side of this boundary. Now, to understand, to physically motivate the existence of this feature, we need to remember that as we move from these hot stars to the cooler stars at the fully convective boundary, the convective zone is getting deeper toward the center of the star. So we know that convection occurs over this typical timescale, which we call the convective overturn timescale. So what this means is that as you approach the fully convective boundary, your convective overturn timescale is getting longer. Now, in our breaking law, we need to scale the magnetic field. And in this breaking law, we have chosen to scale the magnetic field linearly with Rossby number, which is the ratio between the rotation period and the convective overturn timescale. So what this means is that as we approach the fully convective boundary, the convective overturn timescale is getting longer, which also means that the magnetic field is getting stronger. Now, the stronger the magnetic field, the longer the lever arm for the torque, and therefore the more efficient magnetic braking is, which causes rapid spin down at the fully convective boundary. The reason behind the sharpness of this feature is related to the helium-3 instability. You might have heard this as the convective kissing instability. So essentially, stars at the fully convective boundary are undergoing non-equilibrium helium-3 burning. And what happens is that there is an interaction between the convective zone of the core and the convective zone of the envelope. So during these fully convective episodes, the convective zone boundary jumps from a partially convective configuration toward the center of the star. And so this causes jumps in the convective zone boundary, which means jumps in your convective overturn timescale. Now, a natural question that we might ask is, does this rotational feature correspond to an activity feature at the fully convective boundary? So as we have already seen, activity scales with Rossby number as indicated here, which means that you expect to see higher activity as you move toward lower values of Rossby number. And here I'm showing you how Rossby number changes as a function of effective temperatures according to our model, which are color-coded by the age. So what you see is that at the fully convective boundary, there is a change, there is a sudden decrease in Rossby number, which is followed by an increase in Rossby number. And this change is happening over a very narrow temperature region. So this change in Rossby number should correspond to a brief period of higher activity. However, it will be not distinguishable in a mix of stellar populations because of the current uncertainties that we have on the observed temperatures. What this plot is also showing you is that the relation between the Rossby number and the effective temperatures is relatively flat on either side of this boundary. So we interpret this as the lack of a significant change in activity between a partially convective star and the fully convective stars in the vicinity of this boundary. So to summarize, we are showing that the abrupt change in stellar spin down at the fully convective boundary is related to structural changes happening in stars at this location. And we're also showing that this feature does not correspond to a large anomaly in magnetic activity. And if you want to learn more about this work, I encourage you to take a look at our paper. And now I'm happy to take questions. Thank you. Yeah.
There are still a number of MMORs that are below your 10 feet or above your 10 feet line. Does this suggest there's things you're not going to capture all the time?
Yeah, that's right. So the question is, there are a few M dwarfs that are still outside the range shown by these gyrotrons, and what is the reason behind that? So thank you for that question. So there are several reasons, actually. So it could be, first of all, there are periods are wrong. It could be also, for example, on the white dwarfs age side, it could be that some of these stars are just attached the wrong age, and so we don't catch them with these gyrotrons. Something else that, for example, for the stars, they're closer here, they're closest to these gyrotrons. One way to move them around would be to apply things like spots or metallicity to our models. And so we have done that, and what that does is that effectively changes a bit the location of your boundary. So there could be a few reasons behind that.
That's another question. Back there.
Stephanie Douglas, Market College. So you're using upper snow as your initial condition.
Yeah.
There are some unusually slow outliers at a range of masses in upper snow. So does your, right, if you're worried about that upper limit, does your whole, right, so could those outliers just be, you're tracking what the, those very slow outliers are doing?
So this one's here.
Right, so you're using the 50th percentile?
Yeah, we're using the 50th percentile.
At like 9th percentile slow rotator, would you include those outliers, or have you thought about changing your varying nerve?
So we have thought about changing the initial conditions, and initially, actually, what we were doing, we were using the 10th percentile, the 50th percentile, and the 90th percentile to kind of catch that range. But what we found out is that really it was best to take the median percentile and only use that to fit the stars that already converged on the rotational sequences of the clusters. And so by doing that, hopefully we're catching things that are not at the extremes of these initial conditions. Yep.
Okay, thanks a lot. Yeah, I think they were all the questions.